Let's take a look at this unit. Our first section is about the rectangular coordinate system and graphing utilities. And first topic is plotting points on a rectangular coordinate system. Now, a rectangular coordinate system looks like this, where we have our x-axis, we have our y-axis, and we also have where they cross. This is referred to as our origin. Now we have quadrants also. This is quadrant 1. This is quadrant 2. This is quadrant 3. And this is quadrant 4. Now if we were to plot points, for example, if I want to plot this point here, a point has parentheses around it, and the first part is your x part, and the second part is your y part. Now as you go to the right on your x-axis, these values increase. 1, 2, 3, 4, so on. In terms of your y values, as you go up, they increase. Now for your x-axis, as you go this direction, as you go to the left, they decrease. So that's -1, -2, -3, -4. And same thing as they go down. I won't write them out because they're just kind of too many numbers there. But this will be -1, -2, -3, -4. Now if I want to plot the point 2, 3, I'll look at the intersection of 2 on my x-axis and 3 on my y-axis. And where they intersect is where my point would go. Now that's just plotting points in rectangular coordinates. Let's take a look at the distance and midpoint formulas. Let me clear this off. Given 2 points, x1, y1, and x2, y2, then your distance formula is going to be d is equal to the square root of y2 minus y1 squared plus x2 minus x1 squared. For example, if I got 2 points, -3, -1, to -7, and the question was to find the distance between these 2 points. First thing I'll do is go through and label them. This is my first point, so I'll label this as x1, y1. This is my second point, so I'll label this as x2, y2. It actually doesn't matter which one you label as your first point, which one you label your second point. It gives you the same answer either way. Now I'll go through my distance formula, and I'm going to go through and replace all my variables with sets of parentheses. Now since these already have parentheses here, I'll make those a little bit bigger. So we're going to have parentheses minus parentheses squared, and we'll have parentheses minus parentheses squared. This is especially beneficial if you mess up on signs. Remember, this is our y2, this is y1, this is x2, and this is x1. y2 we said was -7, y1 is -1, x2 is 2, and x1 is -3. So we're going to have -7, negative becomes positive. And over here, we got a negative becomes positive. -7 plus 1 is -6 squared. And 2 plus 3 is 5 squared. And -6 squared is 36 plus 5 squared, which is 25, which gives us 61. Now normally we would try to simplify our square root, but that doesn't simplify, so that'd be our answer. Now let me clear that off and we'll look at the midpoint formula. Now still the same setup, given those 2 points. Then our midpoint is going to be x1 plus x2 divided by 2 and y1 plus y2 divided by 2. So if we got 2 sets of points again, let's say I got 3, -2, and 5, -7. Well, if I label them, this is my first point, so I'll label this as x1, y1. This is my second point, so I'll label this as x2, y2. But nobody messes up in the midpoint formula, so there's probably no need to put extra parentheses in with this. Midpoint, you're going to add together your x parts. So I got 3 and 5. Then you divide by 2, and you add together your y parts, -2 and -7. Then I'll divide by 2. 3 plus 5 is 8, so I got 8 over 2. -2, -7 is -9 over 2. And 8 over 2 is 4, and that gives us -9/2. And that would be our midpoint. That would be the point exactly in the middle of those 2 points. Now, next topic is graphing equations by plotting points. Let's clear this off. And I'm going to show this by an example. Let's say I'm trying to graph y is equal to 3x minus 1. I'm going to build something called a t-chart, and I want to choose x values. It's your choice what you want to pick. You probably don't want to pick values too extreme, like 1,317,000. So I'll choose -1, 0, and 1. Now, for each one of those, for the example, the x equals -1, I'm going to plug that into my what I'm trying to graph. This y is equal to 3x minus 1. So plug that into this equation, and I got 3 times -1 minus 1. 3 times -1 is -3 minus 1. That should be a minus 1. -3, -1 is -4. Now plug in x equals 0. Again, I'll plug that in here. So I got y is equal to 3 times 0 minus 1. 3 times 0 is 0 minus 1, which gives us -1. And if I plug in x equals 1, I'm going to have y is equal to 3 times 1 minus 1, 3 minus 1, or 2. Now after we get our points built in our t-chart, then we're going to plot them. -1, -4, be right there. 0, -1, be right there. And 1, 2 would be right there. And then I'll draw a line through them, and that would be our graph. Part of the problem with plotting points is you really need to know what the graph looks like before you begin plotting your points. And I'm just going to generally give you an idea. Let me clear those off. We're going to use this concept I'm talking about right here once we get down to transformations of graphs. This is recognizing the basic functions, but it's used up here if you're plotting points. So our basic functions, graphs, we'll talk more about what a function is. We got y is equal to x. Well, you may have other numbers with it, but basically if you have y is equal to x, it's a line. And we saw that in the example we just did. If you have an x squared of some sort, then you'll have a U-shaped graph, or it could be opening down. If we have y is equal to x to the third, you might have a graph that looks something like this. Now, it'll do different things based upon what else is with it. For example, this is also a graph of y is equal to x to the third, but it has some kind of curve like that. Oh, this isn't the same though. This would be y is equal to x to the third, and then you have other stuff like minus 5x squared plus 7x minus 2. If you got a square root of x, it would look something like this, some form. If you have y is equal to the cube root of x, it would look something like this. And if you have y is equal to the absolute value of x, the absolute value gives us a V-shaped graph. And it'll look like that. And again, we'll talk more about those later on in this recording. Now, let's say I'm trying to graph y is equal to x squared. Let's say I had something like this. Y is equal to x squared minus 7x plus 2. And I'm building a t-chart. And this is the only thing that I see in my t-chart. Since I don't see the U-shaped graph, that means I need to do more points. Because you have to have a U-shape of some sort. So again, this is kind of gives you a guideline on what does graph look like. Now, if you do have a TA3, TA4, we'll talk more about that here in a second. It says identify X and Y intercepts. So let's talk about a little bit about what those are. Not sure why my screen turned green there. Okay. Now, x-intercept, this is where the graph crosses or touches the x-axis. The y-intercept is where the graph crosses or touches the y-axis. Now, to find the x-intercept algebraically, so finding x-intercept algebraically, step 1, you plug 0 in for y, and step 2 is you solve. This is a linear equation like we saw before. Now finding the y-intercept, and again this is algebraically, you plug 0 in for x, and then you solve. It's always the same. When you find an intercept, you always plug 0 in for the other variable. Now this comes in handy because in some problems I'm going to combine this. I'm going to show you how to find the intercepts and graph using intercepts. So if I have, 2x plus 3y is equal to 12. And let's say I want to graph this using intercepts. Well, let's take a look at finding the x-intercept. We said plug 0 in for y and then solve. So we're going to have 2x plus 3 times 0 is equal to 12. 3 times 0 drops away, and we got 2x is equal to 12. Divide both sides by 2, and you get x equals 6. Now intercepts are written in this form, 6 comma 0, and that would be our x-intercept. Now our y-intercept. Plug 0 in for x and then solve. Always plug 0 in for the other variable. So I'm going to have 2 times 0 plus 3y is equal to 12. 2 times 0 drops away. We got 3y is equal to 12. Divide both sides by 3 and we get y is equal to 4. So this would be 0, 4. Some people like the intercept method for graphing because when you plug 0 in, it makes it a lot easier. So 6, 0. It'll be right there. And 0, 4 will be right there. And then you draw a line through. Works fairly well with lines. Sometimes it doesn't work so well if it passes through the origin. But if you have a graph that's a U-shaped graph, it could be when you graph it, it looks like this. So if you were trying to use intercepts to graph that, the only intercept you'd have is 1 point. You'd have no clue what the graph looked like. So it doesn't work in every case for graphing purposes, but you'll see different places in algebra where you need to find your intercepts. Now, last topic in this section is to graph equations using a graphing utility, and I'm going to introduce a little bit of those. You can watch a YouTube video to see more in depth on that. If I want to graph y is equal to x, well, you go to the y equals right here. You can see in red what button I push. This is where you put in whatever you're trying to graph. Clear clears out whatever's on the line, and I push my x key, and then graph. And that gives you y is equal to x. Now, if your graph doesn't look like this, one of 3 things probably has occurred. If I go back to y equals, you see across the top says plot 1, plot 2, and plot 3. Those should not be highlighted. If by accident you have one of them highlighted, that's what it'll look like plot 1's highlighted. Now, one of 3 things will happen if you press graph at this point. One of them is it'll work just like normal, which I guess is what mine's going to do. Another thing is it'll give you a syntax error. If it does, just press enter on the quit. And third thing is it'll put extra boxes on your screen. But either way, if you go back to y equals, you do not want any of those highlighted. If any of them are highlighted, you simply do your up arrow, and if necessary, the right arrow to put your flashing cursor on whichever one's highlighted, and you press enter one time. The second item is your zooming may be messed up. If you press your zoom button and you choose 6 for Z standard, that'll set it back to your standard viewing window, which is -10 to +10 on both your X and Y axis. And then the last item is occasionally you'll have extra garbage on some of these lines down here. For example, down here Y8 or Y9, if I keep going down, maybe you'll have extra garbage down here. This doesn't happen too often. Let's say I have that. Then if I press graph, it gives me syntax error. We like syntax errors. If it gives you the option to choose go to, you always choose go to, because that'll take you where the problem is. It'll actually go down where the line is, and you can press clear to clear that out. And then graph. Now, I'm going to go through our basic functions just so you see it. Our second one was y is equal to x squared. So if I press y equals, press clear, and then you do your x key, and then you push this x squared button here. The x squared doesn't put the x on there for you, so you have to put it first. It just puts a squared on there. And then I press graph. Now the y is equal to x to the third. If I press y equals, clear, and then I do x caret 3. Now this is an older T84. If you got a newer T84, when you do the caret, it puts it up in exponent mode. So it looks like an exponent. You don't see this little caret looking symbol here. If you have one of those calculators, you have to remember to get it out of the exponent. You have to press your right arrow key. And then press graph. Now if you don't press your right arrow key, it'll work just fine on this graph. But if you have anything else that follows it, it'll put everything up in the exponent. Now square root. I do a y equals. Square root is above your x squared. So if I do my clear, I do my second button, and then the x squared, it'll put the square root on there. And I'll put the x key on there. Those are the newer T84. Again, it'll put what looks like a square root symbol on your calculator. You have to press your right arrow key to get it out of the square root, if you got anything more that follows it. And then we press graph. Now the next one is the cube root. So press y equals, press clear. I press my math. and we want to choose a cube root. If you don't see something on a button or above a button for graphing purposes, it's probably going to be underneath this math button. And I can down arrow to the cube root and press enter on it, or you could simply press the numbers in front of it, the 4. And then I'll put my X key in, and then graph. Now our last one we looked at was the absolute value. So if I press my Y equals, clear, again it's not on a button, it's not above a button, so it'll be underneath math button. So press math, right arrow to num, and you see our ABS is our first one. So I choose it, choose X, and then graph. And that's our V-shaped graph. Now section 2.1. Let's take a look at circles, section 2.2. And they're talking about the standard form. So our circles, if you got it in this form, x minus h squared plus y minus k squared is equal to r squared. Now this will be x minus a number or x plus a number, so it doesn't have to actually be a minus, then squared. And this will be either y plus a number or y minus a number squared. Equals a number over here. Then it's in standard form. So that's our standard form. And if you got in that form, then you can identify where your center is. Your center will be HK, and your radius will be R. Now they're saying to write an equation of a circle in standard form. What that implies is that they already give you the center. So let's say the center is 3, -1. And they give us a radius. Say the radius is 4. Now given that information, then we want to write the equation of a circle in standard form. So if they give us a center, they're giving us h and k. This will be h, and this will be k, and the radius is going to be our r. Now we're going to plug them into our standard form, so I'm going to have x minus h we just said was 3, squared, plus y minus k, and k was -1, squared, equals r squared, so that'll be 4 squared. Then you do a little bit of simplifying. So we got x minus 3 squared plus a negative becomes positive. So we got y plus 1 squared, and 4 squared gives us 16. Now this is our standard form. Then it says write the general form of an equation of a circle. Well, general form means you get rid of the parentheses. So let's start there. X minus 3 squared is x minus 3 times x minus 3. Y plus 1 squared is y plus 1 times y plus 1 equals 16. X times x is x squared. X times -3 is -3x. -3 times x is -3x. -3 times -3 is 9. That's FOILing. First terms, outer terms, inner terms, last terms. Y times y is y squared. Y times 1 is 1y. 1 times y is 1y. And 1 times 1 is 1. Equals 16. So we're going to have x squared. We'll put the y squared right next to it. Typically, in general form, you put the squares together. -3x, -3x is -6x. 1y plus 1y is 2y. So you put the x and y terms together. Then our numbers, we got 9 plus 1, which is 10, equals 16. Now you have to see what they say for standard form here. Some books will want the number on the right side, and most of them want it on the left side. So I'm going to take that 16 and move it over. So we're going to have x squared plus y squared. And I think I live next to a train yard. So we got x squared plus y squared minus 6x plus 2y, and 10 minus 6 is negative 6 equals 0. There's different variations of general form. Like I said, some have the number on the right side. Some claim you cannot have any number in front of your x squared and y squared. And then some claim that you can't have any fractions. It'd be nice if there was one standard definition of what is standard form or general form, but unfortunately there's now standard form is a lot more consistent. Now section 2.3. This gets into functions and relations. The first thing we're going to talk about is how to determine whether a relation is a function. Relation just means you're tying two items together. Let me clear this off. And definition of a function. A function says for every x there is only one y. It's a hard definition to work with. It really only works well for points. We got an easier definition of a function. It says if you have one of the following, it is not a function. If you have y to an even power, if you have the absolute value of y, if you have a plus or minus symbol, or x is equal to a number, like x is equal to 3. For example, if I had, and the question whether it's a function or not, if I have y squared minus 3x equals 7. The fact that it has a y to an even power would mean that no, this is not a function. Now if I had y is equal to x squared minus the absolute value of x, we said we can't have y to an even power. We can have x to an even power, so that's fine. And this is y to the first, which is odd power, so that's okay. Absolute value of x. Well, we said that we can't have absolute value of y. We can have an absolute value of x, so that's okay. So this one would be a function. Now if I have this, y is equal to negative square root of x plus 1. We didn't say anything about square roots. Now what this plus or minus symbol means here, you can have a plus, you can have a minus. You just can't have this plus or minus symbol. So this one would be fine. That's a function. On the other hand, if I had y is equal to plus or minus square root of x plus 2, for example, the fact that we have the plus or minus symbol means no, this is not a function. So again, these items you see right here are the exclusions. These are the ones we cannot have. Now this is talking about applying function notation. Let me clear this off. And so let's talk about function notation. Function notation has two purposes. One is to give it a name. Well, what in the world does that mean? Let's say I had two problems here. Y is equal to 3x plus 1 and had y is equal to 5x minus 2. If I told you to graph y, well, your question would be, well, which one? There's two y's on the screen there. So instead of calling it y, I give it a name. Now we don't give it a name like Bob or Bill or anything like that. This one I may call it by this name. How you read that is f of x. There's no mathematical meaning there. That does not mean f times x is just a name. Or we get even lazier in math and we call it f. Now this one over here, I can call it g of x. And we get even lazier and call it g. Now the y and the function notation are interchangeable. So if you want to go back to graphing and you rather have a y there, you can put a y there. If you have y and you want to put the function notation, you can do that. So those are interchangeable. And those letters you just pick as random. When you get into certain application problems, that's where you pick something that makes sense. C of x for cost, R of x for revenue, and so forth. Second purpose of function notation is to reduce writing. What I mean by that is if we got an example where we say evaluate y is equal to 3x minus 1 for y when x is equal to 5. Well, we'd have y is equal to 3 and we'll put 5 in for the x. So that gives us 15 minus 1 or 14. So that's probably a problem you've seen in the past. We're just plugging 5 in for the x. Instead of writing all those words, we could say f of x is equal to 3x minus 1, and we'll say find f of 5. That says the exact same thing as all those words. So we'd say f of 5 is equal, and it's actually solved the same way. We plug 5 in for the x, 15 minus 1, or f of 5 is equal to 14. So again, it's a method of reducing writing. Now this is called evaluating a function. So let's look at our steps for evaluating a function. Step 1. Replace all variables with sets of parentheses. Step 2. Plug in whatever we are evaluating for into the parentheses. Step 3 is to then simplify. So if I had a problem that looked like this, f of x is equal to x squared minus 7x plus 1, and we want to find f of 2. Now whatever's inside of parentheses right here is whatever we are evaluating for. It could be a number, it can be a variable, it can be anything. That's why I say whatever we're evaluating for. And remember our steps. Our first step is to go through and replace all of our variables with parentheses. So I got parentheses squared minus 7 times parentheses plus 1. Notice everything else remained exactly the same. I just replaced the x's with parentheses. Step 2, inside of those parentheses, we plug in whatever we're evaluating for. And that'll always be whatever's inside of parentheses right here, which is 2. So put 2 here and 2 here. And then step 3 is we want to simplify. 2 squared is 4, minus 7 times 2 is 14, plus 1. 4 minus 14 is negative 10, plus 1 is negative 9. And that would be our answer. And that's evaluating a function. Now we already talked about determining the x and y intercepts of a function. Again, that's plugging 0 in and then solving. Now, let me show one more example of that, though. Let me clear this off. We looked at two linear examples, but they don't have to be linear. For example, let's say I had this function. F of x is equal to x squared minus 8x plus 12. And my instructions were to find the x and y intercepts. Now remember, to find the x-intercepts, you plug 0 in for the other variable. So I plug 0 in for y. You might say, well, there is no y. But remember, f of x is the same as y. So we got 0 is equal to x squared minus 8x plus 12. Now this will factor using the PST. So this factors as x minus 2 times x minus 6. Now, zero factor property says you get 0 on one side, you factor the other side, you set each factor equal to 0. So I'll set x minus 2 equal to 0 and x minus 6 equal to 0. And that gives us 2 and 6. So this point would be 2, 0, and this would be 6, 0. Now for our y-intercept, you always plug 0 in for the other variable, so I plug 0 in for x. I'm going to replace the f of x with y. Remember, they're interchangeable, the f of x and y. So I got 0, y is equal to 0 squared minus 8 times 0 plus 12. 0 squared drops away, negative 8 times 0 is 0, that drops away, so we got y is equal to 12. So this point would be 0, 12. And those would be our intercepts. Now determine the domain and range of a function. Let's talk about that. Specifically, I'll focus on domain. Domain's an important part. Range is often determined by looking at your graph. So domain of a function. In general, the domain of a function is all real numbers, except ones that cause a denominator to equal 0, and ones that cause a negative number inside of a radical with an even index. Now finding the domain of a function with variables in the denominator. Step 1, set the denominator equal to 0. And step 2 is solve. And step 3 is either put a slash through the equals or write in interval notation. Now we also have finding the domain of a radical with an even index. You set what is under the radical greater than or equal to 0, and then you solve. For example, if I had f of x is equal to 2 over x squared minus 9, and instructions were to find the domain. Well, this is a function where you have variables in the denominator. Step 1, set your denominator equal to 0. Step 2 is to solve this. Well, this factors. This is the difference of two squares. We've got two terms minusing it. So that factors as x plus 3 times x minus 3 equal to 0. Now, zero factor property. You get 0 on one side, you factor the other side, you set each factor equal to 0. So I'll set x plus 3 equal to 0 and x minus 3 equal to 0. And then solve those and we get negative 3 and positive 3. Now these are our exclusions. These are values we cannot have. If I plug those back in my original problem, they cause the denominator to equal 0. So you put a slash with equals, saying x cannot equal negative 3 and x cannot equal to 3. Or if they wanted an interval notation, you'd go from negative infinity to our smallest number, which is negative 3, parentheses on everything, by the way, union, and then our smallest number to our largest number, so negative 3 to 3, union, and then our largest number to positive infinity. And that would be our interval notation. Now if I had a square root, radical with an even index. Remember, your index is whatever number's in the slot right here, and if there isn't a number there, it's by default 2. So to find our domain, you take what's underneath the radical, step 1, and set it greater than or equal to 0. And then step 2, you want to solve that. So you take the 2 over, it becomes a negative 2, divide both sides by 3, and you got x is greater than or equal to negative 2/3. Or if they wanted an interval notation, I'd put a bracket because there's a line underneath. And I'd go from negative 2/3 to positive infinity since it's greater than. Interpret a function graphically. That's just where you kind of look at it and you see what your domain, range, and x and y intercepts are equal to. Now section 2.4. Linear equations in two variables and linear functions. And I'm going to combine this with section 2.5, so the next topics I'll talk about will deal with those. Let me grab a drink here. We have something called slope. And that says, given 2 points, x1, y1, and x2, y2, your slope is going to be a change in y over change in x. So you're going to have y2 minus y1 over x2 minus x1. For example, if you're given negative 3, negative 8, and negative 1, and negative 2. This is my first point, so I'll label this as x1, y1. This is my second point, so I'll label this as x2, y2. Now I'm going to go to my formula for slope, always represented by little m, and everywhere I have a variable I replace with a set of parentheses. So y2 minus y1, so parentheses minus parentheses, and x2 minus x1. And then you plug in what you identified. y2 is negative 2, y1 is negative 8, x2 is negative 1, and x1 is negative 3. Now negative negative becomes positive, so we got negative 2 plus 8 over negative 1, negative negative becomes positive. Oops. Negative 2 plus 8 is 6, negative 1 plus 3 is 2, which gives us m is equal to 3. And that'd be our answer. Let me erase that. We have something called slope-intercept form. And slope-intercept form means we got y is equal to mx plus b. You could have f of x there, because remember they're interchangeable. It could be f of x equals mx plus b. Now if you have it in this form, whatever number is in front of your x is your slope, and whatever number is at the end is your y-intercept. Now, having it in this form helps you graph by hand. For example, if I have y is equal to 1/2 x minus 3. Slope-intercept form means you have it solved for y, and everything's the first power. Now this is going to be our slope, the 1/2. And this is a change in y over change in x. This is a positive 1, so that means we're going up 1. This is a positive 2, which means we're going right 2. If this was a negative 1, we'd go down 1. If this was a negative 2, we'd go left 2. Now here's our y-intercept. So to graph this, darn train. Wife's got it 100 degrees in here and trains going by, so I can't have my window open. If I pass out, call 911. Y-intercept is negative 3. So I'm going to go put a point first at my y-intercept at negative 3. Now from that, I'm going to use my slope to get my second point. So starting from this point, I'm going to go up 1 and right 2, and that'll be my second point. Now after you have those, and you draw a line through them, and that'll be our graph. Much preferred method versus the t-chart. Let me clear that off. Now some problems revolve around finding the let me get that off there. Finding the equation line. When I say find the equation line, you're talking about slope-intercept form. So finding the equation of the line. Now step 1 is to find m. Step 2 is to plug the given point in for x and y, and m from step 1 into y equals mx plus b, and solve for b. And then step 3 is to write your answer. Plug in m from step 1 and b from step 2 into y equals mx plus b. So for example, if I have m is equal to 5 and it passes through the points negative 1, 2. Step 1. Find m. Well, that's easy. This one's given. It may not say m, may say slope equals 5, but same difference. Step 2. Plug in the given point for x and y. When they give us a point, they're giving us a specific instance of x and y that we can use. So I'll plug that in for x, and I'll plug that in for y. So we're going to plug 2 in for the y. M we just said was 5, and x is negative 1, plus b. And then we want to solve for b. 5 times negative 1 is negative 5. Take negative 5 to the left side, and you get b is equal to 7. Step 3. Plug in m from step 1, which is 5, and plug in b from step 2, which is 7. And our answer will be y is equal to 5x plus 7. Now let's say, instead of that information, we're given negative 1, negative 3, and 5, negative 2. And same instructions. Want to find the equation of the line. Well, step 1, instead of m being given directly, we have to use our formula. Remember, our formula is y2 minus y1 over x2 minus x1. This is my first point, so this will be x1, y1. This is my second point, so this will be x2, y2. So we'll plug in our values. y2 we said was -2, y1 is -3, x2 is 5, and x1 is -1. We got -2, negative becomes positive. And down here we have negative, which becomes positive. -2 plus 3 is 1, and 5 plus 1 is 6. So m is equal to 1/6. Now step 2 says to plug in a given point. We got 2 points. It's your choice on which one you want to use. Whichever one looks easier to you is the one you choose. I pick the second one. As weird as it seems, they both give you the same answer. So I'm going to plug -2 in for the y. M we just said was 1/6, and x is 5 plus b. 1/6 times 5 is 5/6 plus b. Take 5/6 to the left side, it becomes a -5/6. Now this is a mixed number rule. -2 times 6 is -12, plus a -5 gives you -17, and then your denominator stays as is. And then step 3, we want to write down our answer. So we'll plug in m from step 1, which is 1/6, and we'll plug in b from step 2, which is -17/6. And that would be our answer. Now we have the condition where we're finding the equation of the line given a point and either a parallel or perpendicular line. So step 1, we want to find m. And our first substep within that says to write the given line in slope-intercept form. Solve for y, basically. Our second substep says to identify the slope. And then see if they're parallel lines. Parallel lines have the same slope. If it's perpendicular, perpendicular lines have slopes that are negative reciprocals. Now step 2, plug in the given point for x and y and m from step 1c into y equals mx plus b and solve for b. And step 3, write your answer. And I won't write that down because I'm at the end of the page. But remember that, so plug in your m from step 1c and plug in your b from step 2 into y equals mx plus b. Let me clear this off. So let's say I had the point 1, 2, and it's parallel to y is equal to 5x minus 2. Now step 1, we want to find m. The first substep says to write the given line in slope-intercept form. This is already in slope-intercept form. It's already solved for y. Our second substep says to identify the slope. If it's in slope-intercept form, whatever number's in front of your x is your slope. So slope is 5. Now we said parallel lines have the same slope. So we said it's parallel to y is equal to 5x minus 2. We said the slope of that is 5. So the m we're going to find is going to be 5 since parallel lines have the same slope. Step 2. Plug in the given point. Remember that's x and that's y. So put 2 in for the y. M we just said was 5, and x is 1, plus b, and then solve for b. 5 times 1 is 5, but take it to the left side, becomes a negative 5. And you get b is equal to negative 3. And then step 3, plug in the slope from 1c, which is 5, and plug in the b from step 2, which is negative 3, and our answer is y is equal to 5x minus 3. Now let's say I have the point 1, 3, and it's perpendicular to 2x plus 3y is equal to 7. And step 1. Oh, instructions are still the same. Find the equation line given those conditions. Step 1, first substep, write the given line in slope-intercept form. This one isn't in slope-intercept form, so I want to solve for y. So I take 2x over. We get 3y is equal to negative 2x plus 7. Divide everything by 3. And we get y is equal to negative 2/3 x plus 7/3. Now our second substep says to identify our slope. So slope is negative 2/3. It's whatever number's in front of your x. Now C. Perpendicular lines have slopes that are negative reciprocals. What that means is we're going to start with the slope from 1b, which is negative 2/3. We're going to write it in fraction form. Well, this is already a fraction. But imagine you had 5. You put 5 over 1. You can always create a fraction by putting it over 1. And then we're going to flip it. Top goes to bottom, bottom goes to top. That's what reciprocal means. Reciprocal means fraction flipped. And then we're going to change its sign. So it goes from negative 3/2 to a positive 3/2. That's what it means to be a negative reciprocal. Write it in fraction form if it's not already there. Flip it, change the sign. So the m we're trying to find is going to be 3/2. Step 2. Plug in a given point. Remember that's x and that's y. So we got 3 for the y. M we just said was 3/2. And x is 1 plus b. And then solve for b. Well, 3/2 times 1, 3/2. So I take it over, it becomes a negative 3/2. And this is again a mixed number rule. So I take 3 times 2, which is 6, plus negative 3, which gives me 3/2. It's kind of weird. Did I do that right? 3 times 2 is 6, minus 3 is 3/2. Yeah, I guess it would be. That just seems bizarre. Okay. I make these up. I don't plan them ahead of time. And then we write our answer. So we plug in m from 1c, which is 3/2. And plug in b from step 2, which is 3/2. Boy, that just seems just as bizarre as can be. So they both came up 3/2. Okay, and that'd be our answer. Another train. Now they talk about linear regression here, so let me just show that real quick, just so you see how to do it on the calculator, because I don't think I have that in any of the videos. Clear this off first. if I have a set of points. And they may not be on a straight line, so don't think that has to be true. And this is -5, this is 0, and this is 7. And I want to create models using linear regression. Well, first thing I'm going to do is put these in my calculator. You can get out of anything in your calculator by doing second mode. And then I'm going to press my stat button right here. And I want to do enter on edit. You may or may not have numbers here. If you have any numbers there, you can press your delete to clean them out like that. There's quicker ways to clean those out, but since we're giving you accelerated lecture, I won't show you the easy way. We'll clean those out. Then 1, 2, 3. So 1, 2, 3. I put my x values in L1. Then I right arrow over to L2, and I want to put these values, -5, 0, 7. Now each time I press enter, it goes down to the next line. Now I'm gonna exit out. So I do second mode. You only have to do this one time, but we want to set our diagnostics on. So I do second 0 to go into my catalog. Then I'm push my X and -1, go down to the D's fairly fast. Or you can just simply press your down arrow over and over until you get to it. But I want to choose diagnostic on and press enter. Now if I do stat, right arrow to calc, and I want to choose the fourth one, linear regression. You can down arrow to it and press enter, or choose 4 and then press enter again. Now the A and B you see here, you'd plug into this equation up at the top. So it tells us A is 6, I'll put 6 in for the A. It also tells us B is -11.333, a bunch of 3's. I'll take it to 2 decimal places, but that'd be a -11.33. This would be the model that they're talking about. This is a horrible process to do by hand. Technology is the best way to do it. Now the R is how good it is. The closer it is to +1 or -1, the better the line is. So if this had said that R is equal to 0.0315, that'd be horrible. But since it's fairly close to 1, that means this is a pretty good model. Okay, now transformations of functions. So let's talk about these. Now I'm going to give you the quick overview on those. We've already talked about the basic graphs, and I'd like to do these with examples. If you remember our basic graphs, like x squared, that's our U-shaped graph. If you have a number at the very end or at the very beginning, this shifts it up or down. So this means that our basic graph is going to be shifted up 3 units. Now if I look at my basic graph, it was our U-shaped graph. It still looks exactly the same. It just shifted up 3 units now. So it'd look like that. Now on the same lines, if I have a minus at the end, if positive was up 3, then this is going to be down 2. Now the absolute value is our V-shaped graph, remember? It's still going to look like the V-shaped graph, is just shifted down 2 units. So it'd look like that. Now that's our up or down. That's our vertical shift. Let me clear that off. If instead of the number being at the end, let's say the number is inside with the x. What in the world does that mean? Well, inside of parentheses, inside of the square root, inside of the absolute value, inside of whatever we're talking about. If the number's inside with the x, it shifts left or right, opposite what you think. The -3 would make me think goes left 3, because that's where the negatives are. So this is really going right 3. Now this is our U-shaped graph because it's got the x squared. This right here determines the U shape. It still looks like a U-shaped graph. I'm just shifting the entire graph 3 units to the right. So it looks like that. Now if I have y is equal to this right here. Notice the number is inside with the x, so that shifts it left to right, opposite what you think. Plus 2 would make me think right 2, so it's really going left 2. Now our basic graph of the square root, it looked like this. It still looks like that, except for I'm shifting the entire graph left 2 units. Then it would look like that. Those are our horizontal shifts. Let's talk about our reflections. If you have a negative out in front, negative out in front means it reflects across the x-axis. X squared is our U-shaped graph. When I say reflected across the x-axis, that's flipped upside down. It would look like that. Now it's a little bit more than that. You have to think of like an axle in a car. The entire rectangular coordinate system rotates just like an axle. So if you had y is equal to negative x to the third, then you'd have part of it go down, part of it go up. Now instead of the negative being out in front, let's say the negative is inside with the x. This is going to reflect across the y-axis. Now here's our basic graph, square root of x. Again, reflected across the y-axis looks like it's been flipped across the y-axis. But actually the entire coordinate system is rotating around the y-axis. And those would be our main transformations happening. They're shrinking and stretching. Let me just talk about that briefly. Shrinking and stretching is hard to visualize. You really have to plot points or just plug it in your calculator. Now remember our x squared. That's our U-shaped graph. Maybe it looks something like that. Now the y is equal to 2x squared. What that does is 2x squared makes me think it should become twice as big, but it doesn't. It shrinks it in toward the y-axis. It's because the y values are increasing twice as fast. Like that. And y is equal to 1/2 x squared. Again, makes me think it should bring it in so it's half as big, but it actually stretches it out. Different graphs will perform different manners. Now the reason why I don't really like these that well is, did I really graph 2x squared? Probably not. Might have been 3x squared, 4x squared, 5x squared. Probably didn't graph y is equal to 1/2 x squared. The only way you can get an accurate picture is to plot points or plug in your calculator, both of which defeat the purpose of what transformations are truly powerful. It allows you to quickly come up with a graph without picking up a graphing calculator. Okay, let me clear those off. Now these are talking about even and odd functions, and increasing, decreasing, relative min, max, and piecewise functions. And let me show you an example of an even function. This is an example of an even function. And why it's an even function is it's symmetric to the y-axis. Now symmetric to the y-axis means if I were to pick a point here, if I come straight over my graph, let's say that distance is 2. If I come straight over to this point on this graph, this distance will also be true. And that's true for every point on our graph. It's equal distance from the y-axis. Now, from a practical standpoint, to solve those problems, what you do is, if you got the graph, if you can take the right side of the graph, the right side of the y-axis, flip it over, reflect it, fold it over, and it lands exactly on this side, that means it's even. Now, algebraic determination for it. What you do is you plug negative x in for x and see if you can get your original problem. For example, if I have y is equal to x squared, let's plug negative x in for x. So where the x was, I'll put in parentheses, and then we're going to put negative x in there. Now we're going to see if we can get it to look like the original problem. If we can, that means it's even. Well, negative x is second power. Negative x times negative x gives us a positive x squared, which equals to our original problem. That's what tells us it's even. Now for our odd function. This is an example of an odd function. And the reason why it's odd, it's symmetric to the origin. Now what that means, I can't draw it very well. But if I draw a line through here, and it touches at this point, let's say that distance there is 5. Well, the straight line here touches at that point, that distance should also be 5. And that should be true for any line you draw that intersects the graph. They are equal distance from the origin. Now from a graphical standpoint, that's easy to solve. What you do is you start with one of your quadrants. Like I start with the first quadrant here. I'm not drawing these very well, but if I start with the first quadrant here, if I flip this across the y-axis, and then if I flip it across the x-axis, the question is, does it land exactly on this part of the graph? If it does, that means it's odd. Now from an algebra standpoint, how you determine it is you plug negative x in for x, and you plug negative y in for y. For example, if I start with y is equal to x to the third, everywhere I have a y, I'll put a parentheses. Everywhere I have an x, I'll put a parentheses. Now we're going to plug negative y in for y. So I'll put a negative y where the y was. And we'll plug negative x in for the x. Now the question is if you can use algebra to get this to look like the original function. We've got negative y, negative x to the third power. Negative x times negative x is a positive x squared, times another negative x is negative x to the third. If I divide both sides by negative 1, I'm going to get y is equal to x to the third, which is equal to our original function. And that would be how you determine algebraically if it's an odd function. Let me erase those. And let's look at an increasing, decreasing, constant function. There we go. Okay, now originally, clear over here, by the way, is negative infinity, and this is positive infinity. So originally it's constant, it's going straight across. And we only use x values when writing our answer. And everything has a parentheses on it, it's open intervals. Okay, so this is going from negative infinity, and it stops being constant right here. If I come straight up to my x-axis, that's negative 2. And then my graph is increasing, it's going up. So it's increasing from negative 2. Now it stops increasing here. If I come straight down to my x-axis, that's positive 1. And then it's decreasing. So it's decreasing from 1 to positive infinity. And that's our increasing, decreasing constant. Let's say I have this graph, as well as I can draw it. And the question is about relative extrema. How that's spelled. Relative extrema. That means mins and maxes. This right here would be a relative max. Now, relative max is when your graph changes from increasing to decreasing. Or you can think of it this way. It's a high point relative to what's immediately around it. Now, that doesn't mean it's the highest point on our graph. Since this keeps going up forever, there's an infinite number of points higher than that. It just means it's a high point relative to what's around it. So this would be a relative max, and usually you write it in point form. So that'd be a negative 2, 3. Now this would be a relative min. A relative min is where your graph changes from decreasing to increasing. Or you can think of it as a low point relative to what's around it. And this would be 2, negative 1. And those would be our relative extrema. Now let's talk about function composition. I'm kind of running out of time a little bit, so if I have f of x is equal to 2x minus 1 and g of x is equal to 3x minus 2. Let's say the first thing I want to find is this notation right here. Now this does not mean multiplication. That notation means find the composition of f and g, which is f of g. Now, how I learned it way back when I took college algebra is f was first here, so f is first here. G is what goes second here, so G is what goes second here. It's what goes inside your parentheses. I had a student say, well, I know it's the composition symbol, but can I think of this as of? F of G? Yeah, that's a pretty good way to think of it. Now, this is just evaluating a function. If you were to cover up the G, we're trying to find f of something. So I'm going to go to my f of x, which is 2x minus 1. And where my x is, I put in a set of parentheses. Now, evaluating is always the same. Whatever's inside the parentheses here is automatically what you're going to put in here. So I'll put g in there. But g is equal to 3x minus 2. So this becomes 2 times 3x minus 2 minus 1. 2 times 3x is 6x. 2 times negative 2 is negative 4 minus 1, which gives us 6x minus 5. Now we can find the composition going the other way. We can find the composition of g and f, which is g of f. Again, you can think of the composition symbol as of, g of f. Now this is evaluating g of something. So we're going to go to our g of x, which is 3x minus 2, and where my x was, and I'll put in parentheses. Now evaluating is always the same. Whatever's inside the parentheses here is automatically what you put in here. So I'll put f there. But f is equal to 2x minus 1, so this becomes 3 times 2x minus 1 minus 2. 3 times 2 gives us 6x. 3 times negative 1 is negative 3 minus 2, which gives us 6x minus 5. Not every problem will have these look exactly the same. And then one other item that's notation. You may run across a problem looks like this. What this is saying doesn't say take the composition of f and g times 2. This says first find the composition of f and g, which is what we just did over in this part. And then you're going to plug 2 in for the x. So I got 6 times 2 minus 5 gives you 12 minus 5, or gives you a 7. Now I'm going to go ahead and stop the recording here, and then I'll answer any questions you might have.